Okay, good morning. Okay, everybody got a seat. Let's get started. So, by now, in principle, you know everything you need to know in order to design control systems for single input, single output linear systems, okay? What I would like to do today is go over some of the things that happen in reality, but are ignored typically when you do your linear design. Okay, so things that we have ignored up to this point. So things that we have ignored up to this point, but they are things that you need to take care of, okay? So, so this is what I call nuisances, okay? Okay, so the first one that we talk about is time delays. Where do you think that time delays come from? No idea. Typically what you have, how do you implement your controller? Nowadays, it's most commonly done on some kind of like a microcontroller, right? So like a small microprocessor. They read some, data out of some sensor, run some computer code, computes what the control input should be, outputs that control input to some actuator, right? However fast your microcontroller is, running this computation will take some time, right? So you will have some time delay in which the control action is not computed based on the current value of whatever output you're measuring, but is based on some past value of the output, okay? Okay, so this is what you will have more typically, okay? So just implementing your, sorry, I had to. Okay, use my finger again. Okay, so one source of these time delays is just running a computer, right, computer code, okay? But other systems you may have that time delays actually come from the specifics of the, of the plant itself. My favorite example to think about time delays is actually how you control the temperature in the shower, okay? So you get in the shower, the temperature is too cold. What do? You take the, whatever knob and you just yank it all the other, the way to cold? No, right? Typically you don't do that. Why don't you do that? I mean, if you have instantaneous feedback, right? So as soon as the water becomes too cold, then you will be able to stop, right? And set the right temperature, right? A high gain controller will be just fine. Why doesn't it work in practice? Or what do you do typically when you're setting the temperature in the water?
You predict the way it's going to change.
In a sense, but if you were just to trust your prediction, then essentially what you will do is change the, the setting on the lever and then just step into it, confident that the temperature will be correct, right? Is that what you do?
Well, you keep changing what you predict as you change.
Right, but when you change it, what you typically do is you do it very slowly, right? Why do you do it slowly? Exactly, right? So as you change the, the position of that lever, right? So that, changes the setting in some valve. So the water that gets into that valve gets mixed up in a different way, but then it needs time to travel up the pipe and down the, whatever thing is called, right, and then hit your body, right? And that may take, I don't know, half a second, 1 second, whatever, right? But then the point is that if you apply the feedback on what you feel now, you will be wrong, right? So then you have to do these things kind of carefully, okay? So this is a particular example of a source of a time delay. This is something that's called a transport delay, right? Because there is some physical object or, some physical, well, in this case, water that has to travel, along the pipe before it hits your body and you can measure the temperature, right? On an airplane, you change, for example, you change the setting in the, in the ailerons, and then, you're on the elevators, and then, something that may happen is that, it changes your lift, may hit your tail, so there is a time delay there. There's, again, due to a transport phenomena, right? And also, this is something that may have an effect on the stability of the airplane. Another example is when you are driving say, a planetary rover on Mars, okay? And you're trying to drive it from here, from the Earth. Well, it takes, whatever, like 8 minutes or something to get, to all the way to Mars and back. So you also, again, have to be very careful, okay? So the point here is how do you take into account the effect of a time delay? So a time delay is an operator, right? So it's something that takes a signal, let's call it the input signal, and transforms it into some other signal, the output signal, which is just the same as the input, just translated in time by some capital T, where capital T is the amount of the delay. Is this a linear operator? Yes or no? Well, clearly yes, right? Because if I take my input signal and multiply by 2, the output signal will just be delayed and multiplied by 2. Okay, so actually the output signal is exactly the same as the input, just with a different time parameterization, okay? So it is a linear system. So in principle, we can use everything that we have learned so far to deal with it, okay? However, there is a, there is a subtlety in a sense here, right? So what is the transfer function of a time delay? Well, let's say that the input has the form u of t is equal to e to the power st, okay? So this is our usual test input, okay? What would be the output? The output will be e to the power s multiplied t minus capital T, okay? Because we are translating everything in time, okay? So you see that the transfer function is e to the power minus st. Okay? This is a perfectly valid transfer function, is a function of S. What is different from every other transfer function that we have seen so far in the course? As you can see, this is not a rational transfer function. This is not a ratio of 2 polynomials. Okay? This is an exponential function. So what are the zeros, what are the poles? I don't know, right? Actually, there are, there are no finite zeros and there are no finite poles, right? Because there is no value of S that will make this thing 0, and there is no value of S that will make this thing infinity, right? No finite value, okay? So this is not a rational transfer function. This is really what creates a little bit of the problems, okay? But let's try to look at, what it means in terms of, for example, of frequency response, right? So, okay, so let's say that this is the input, right? The blue line. The output, if I have a delay of, in this case is what, 2.5 seconds. The delayed version, what you see is just the same wave function, just shifted in time, right? So what can you say about the amplitude of the frequency response? For whatever frequency, the magnitude of the output will be exactly the magnitude of the input, right? So what we have is that the magnitude of the frequency response is 1, period, okay? For all frequencies omega. What is the phase? Well, as you see, the phase is actually given by, in this case, is minus omega capital T, okay? So you see that the phase is delayed by this amount. Okay. Is it clear? Right? Because so well, okay, so you can see it also from here, right? So if we take the magnitude of e to the power j omega t, that's something that stays on the unit circle, yeah?
Yes, why is the phase given by minus omega t and not by inverse tangent function? Usually to
yeah.
the angle.
Yeah. So if I write the complex number e to the power j omega t, where is this guy on the complex plane?
Anywhere, we don't know where it is.
Well, you should know. Come on. This is a complex number, right? You've taken some complex analysis, I guess. Would be on the unit circle, yeah. Mm-hmm. And where on the unit circle? This is not a control systems question, right? So this is just a matter on complex numbers, yeah. So this is the unit circle, right? Right? In particular, this point will be here where this angle here is exactly omega t, right? Okay. So in particular, well, I mean, what you know is that, e to the power j, let's say, j phi, right? So what is this? Or in general, if I have rho times ej phi, what is this complex number? How do you write it in real part and imaginary part? What is the real part of this guy here? Plus, yeah, we're using j, right? Sine of phi, right? Everybody agrees with that? This is Euler's formula, right? So this is not something that you learn in this class. This is something that probably you have heard before. Okay. I can get witnesses for that. Okay. So, right, so this is how you go from this to this, right? And then, okay, so you can also see it from here, right? So what is the phase, what is the argument of this number? This is the real part, and this is the imaginary part, right? So then the phase of rho e j phi will be given by, okay, the arc tangent, or what? Oh, sorry, I forgot. Okay, let's write it like that. Arc tangent of rho sine of phi over rho cosine of phi, right? So which is the arc tangent of phi, right? Which is clearly phi, right? Yeah, so everything like it matches up, right? So we are not making things up. Okay, so this is where the phase of this comes from. Okay. Good. So we can do the same on the body plot. We can do the same on the Nyquist plot, and so what you see is that the polar plot clearly is something that just is on the unit circle, right? So e to the power j omega t is on the unit circle for all values of omega, right? As I increase omega, my point will just move on this circle, okay? What happens on the body plot? Well, the magnitude of the body plot is always 1, that is 0 dB, so it's just a straight horizontal line. The phase is linearly decreasing with omega, right? However, since we are displaying omega on a logarithmic scale, then the phase will actually go down as an exponential, okay? So you can either draw it as an exponential just going down like that, right? Or you can just wrap this, right? So you could technically also do something like this, right? Okay. However, you usually wrap the phase between 0 and negative 2 pi, and so that's why you see all this up and down here. Okay. Clear? This is just the body plot of e to the power j omega t. So, what is the effect of a time delay on your loop transfer function? Okay. So, let's say that you have a loop transfer function, L of s is equal to C of s, your compensator times P of s. We have a time delay of t seconds. Now the new loop transfer function will be given by this L prime of s, which is given by your ideal L of s, times the transfer function, the time delay. Okay? How do you get the body plot of the system with the time delay? The magnitude of the body plot is exactly the same as if there was no time delay. Okay? However, what happens to the phase? The phase plot will be shifted down by this exponentially increasing phase delay. Okay? So, what is the effect of this on your design? What we are doing is say, consider a simple plant. So simple, first order leg, 1 over s plus 1, stable, just one stable real pole, okay, easy. Right, so the ideal transfer function will be this one, right, so given, say, a proportional controller k, okay. So what you can do is, what does the root locus of this thing look like? So you have a pole here at, say, -1. What does the root locus look like for a positive k? Anybody? It goes to infinity, where? To the left, yeah. So for whatever value of k, what you will get is that the closed loop will be stable, okay? Right? Okay. You can see the same for for Nyquist, okay? Now, what happens when you bring in the time delay? Okay, so now our transfer function is no longer k over s plus 1, but will be k over s plus 1 multiplied by this exponential, okay? So what happens is that, okay, so on the Nyquist plot, no longer you have this nice half circle. The way that you can think of it is that for every point on this half circle, you just have to rotate it by omega t, okay? And as you move towards the origin, omega is increasing. So the angle by which you are rotating that point increases, okay? So you can visualize it as you want. I think of this as like a smearing that circle, right? By an amount that is actually increasing the closer you get to the origin. And in fact, what you see is you get this kind of like a spiral, okay? Because as omega gets to infinity, that is when you get closer to the origin, the amount by which you had to rotate those points goes to infinity as well, okay? On the body plot, the magnitude plot is not changed, but look at what happens to the phase plot, okay? And again, when you see this thing going up and down, it's because I'm wrapping the phase between 0 and negative 2 pi, okay? So what does it mean in terms of stability, of closed loop stability? Is this stable for all values of k? No? Right? So think of, where is the, let's say that the -1 over k point, right? -1 over k. Now writing with my finger is even worse than writing with a pen. Okay. So what do you think will happen? Will I be stable for all values of k? Not quite, right? Because as I increase k, what happens to the -1 over k point? We'll go closer to the origin, right? So will I have encirclements? Yeah. How many encirclements? As many as you like, okay? So essentially you can get as many unstable closed loop poles as you like by increasing the gain, okay? Look at what happens on the body plot. So the original transfer function without the time delay, the phase was always between 0 and -90, right? So you will never go to -180. So you thought that, well, I can make the gain as large as I want because I will always have at least 90 degrees of phase margin, right? Now what happens to the phase now? You see that the phase actually does get below -100 degrees very often, and by the way, it gets very much below -180 degrees, okay? So, this is, the effect, right? So in particular, well, I mean, you see it here, right? So the first crossing, of the real axis on the Nyquist plot occurs when essentially the tangent, well, omega satisfies this quantity, right? And essentially what you have is, your phase margin, before it used to be 90 degrees always, now will actually can be reduced to 0, meaning that the gain can only be so much, right? So the gain margin you compute it from when the phase crosses -180, right? And then you see that the phase margin is, say, less than 5 dB in this case, okay? So, this is true for any other transfer function, okay? So what is the main effect of the time delay? The main effect of the time delay is to eat up your phase margin, okay? That's why it's very important when we design our control system. Typically we say, okay, let's make sure that the phase margin is at least 45 degrees, 60 degrees, or whatever, right? So technically, as long as the phase margin is more than 0, your closed loop will be stable. However, there may be things that actually reduce your phase margin in practice. What are those things? The number one culprit in this case is actually a time delay, okay? Whatever computation you do in your microcontroller will cause a time delay. This time delay will reduce your phase margin. So you thought it was 60 degrees, it's now 15 degrees, okay? So the phase margin, including the effect of the time delay, was the ideal phase margin with no time delay, minus what is the phase delay at, by how much is the phase margin reduced? Well, you had to multiply your time delay t by the frequency at which you are computing the phase margin, which is the crossover frequency, okay? So, summarizing this, what essentially you can think of is the following. So the main effect of the time delay is a reduction in the phase margin, and this reduction in the phase margin gets higher and higher as you increase the crossover frequency, okay? So the faster you want your system to behave, right? So for example, you remember that the crossover frequency is an estimate of your closed loop bandwidth, right? So the faster you want to make your closed loop bandwidth, the more of a phase delay you will have, the more of a phase margin reduction you will have for a given time delay, okay? So just be careful, okay? So that's one of the reasons why you may not want to push the crossover frequency or the closed loop bandwidth too much, because then you are exposing yourself more to potential instabilities due to the time delay. Okay? Yeah.
To minimize the time delay, we would have to build our system as rich as possible and to have the best sensors as possible in Ethernet.
To minimize
the time delay, we have to build our system as rich as possible
Why rigid as possible?
Yeah, like when we turn on the water, and there's a lot of wobbly things.
Okay. Right. So well, in that case, what you're trying to say, okay, so it takes some time. So clearly one reason to minimize the effect of the time delay is, in that case, would be to have a shorter pipe, right? Or maybe put the valve right on the shower head, right? Right, definitely. But in that case, you are making the time delay shorter, right? Or, one way of reducing the effect is buy a faster computer, okay? Clearly, buying a faster computer will reduce the effect of the time delay. Do you want to do that? Maybe not always, right? Because a faster computer also means a computer that is more expensive, right? So you may not want to do that, okay? So essentially what you have to do is find the right balance, right? So if you want your system to be very fast, to have a very high closed-loop bandwidth, high crossover frequency, well, you better have a fast computer, okay? I mean, that's kind of intuitive, right? But, that's the truth, okay? Or if you cannot make the computer fast enough, make sure that you have enough of a phase lead so that you can absorb the effect of the time delay without reducing your phase margin too much, okay? Or by making your phase margin too small. Is it clear? So, what could be a possible design procedure? A possibility would be to do something like that. So designing your feedback control system, ignoring the time delay. Then what you do is, you've done your design, you know how fast your microcontroller is, okay? You know how much time it takes to compute the control input, okay? And then you check what is the effective phase margin, that is the phase margin that you get by including the effect of the time delay, okay? Maybe the ideal phase margin was 60 degrees, your effective phase margin is 45 degrees, so you can say, okay, you know what, 45 degrees is still fine, and you're happy with it, and you just run with it. If your new phase margin does not meet your design criteria, then what options do you have? Well, one of the options is to increase the phase crossover. Add a lead compensator, right? So the lead compensator will increase your phase margin, okay? A lead compensator will be a little bit slower to compute, right? Because now, you're making the job of the microcontroller a little bit harder, right? So again, not by much. But so this is one possible option. Another option is to decrease the crossover frequency, okay? Because if you decrease the crossover frequency, you also decrease the phase delay, okay? So you may still get a good phase margin, okay? And that's exactly what you do when you are carefully changing the setting in your shower, okay? So essentially what you're doing is a low gain control strategy, which is also a low bandwidth, low crossover frequency control strategy, okay? So you've been doing this since you were, probably 6-year-old, right? But you didn't realize that you're essentially designing a low gain control strategy to cope with the time delay, okay? Okay, and then, you kind of like iterate, as desired as needed to get the desired behavior, okay? Now, as you may have noticed, what we did so far is we addressed this time delay on the Nyquist plot and on the body plot, right? I told you Nyquist always works. You can always trust it. Body, you had to be a little bit careful. In this case, turned out to be okay. But the other, tool that we used, we looked at the root locus, right? And I said that, the root locus is something that will always give you the correct answer as long as you can use it. This is the problem now. So in our case, how would you use the root locus with this time delay? The time delay, doesn't have a finite zeros and poles, right? So how do you represent the time delay on the root locus? We don't know, right? We don't know how to do that, okay? So the problem here is that the time delay is not a rational transfer function, so we do not know how to represent it on the root locus. So in principle, or to be precise, you cannot use the root locus to design a control system with a time for a system with a time delay. Okay? But let's say that we really want to use the root locus, okay? So something that you can do is take your non-rational transfer function and approximate it with a rational transfer function, okay? So something that you can do is take, e to the power minus st, compute the Taylor series expansion, which is just 1 minus st plus 1/2 st squared, so on and so forth. We can truncate it and, let's say, only maintain the first two terms, okay? Notice that this is a non-proper transfer function, right? With two non-minimum phase zeros. It's already bad news. This would be a good approximation for small st, okay? But something that you may notice is that the magnitude of this approximation of the frequency response goes to infinity as omega goes to infinity, which doesn't sound right? Because we know that the magnitude of the time delay should be 1 at all frequencies, okay? So this is a good approximation for very small omega. Is a rather terrible approximation for omegas that get bigger and bigger, okay? So, well, let's not use this one. A better approximation is something that can be obtained using something that's called like a Padé approximation. The idea of the Padé approximation is instead of approximating your function with just a polynomial, like the Taylor series, what we do is we put a polynomial at the numerator and a polynomial at the denominator, okay? So let's approximate a function by the ratio of two things that look like a Taylor series expansion, okay? In particular, what we will do is just let's limit ourselves to the ratio of two first-order polynomials. So we want to approximate e to the power minus st by some k that multiplies s plus p over s plus q, okay? Just two first-order polynomial, numerator and denominator. I think that we can skip the algebra. So, I mean, if you really want to do it, you can. Essentially what you do it is, what we want to do is that this guy here, that is my Padé approximation, must match the infinite series, right? So the infinite Taylor series is actually the same as the exponential function, okay? And then what you do is you just match up the terms, okay? So you just make sure that the first order terms on this side are the same as the first order terms on this side and the second order term and so on and so forth, okay? So making a long story short, what you get is that, okay, so essentially you solve this system of equations, and then what you get is that the Padé approximation of the time delay is given by this fraction here, 2 over t minus s over 2 over t plus s, okay? So what you see is that this approximation has a non-minimum phase 0 and a stable pole, okay? Something that you may want to check is that the approximation, so this approximation has the advantage that indeed the magnitude of this fraction is always 1, okay? So at least we are getting that right, okay? So, so essentially what you can do is take this approximation and use that to approximate your time delay when you're doing the root locus sketch. In fact, what we get in this case is the root locus will be, okay, so the blue pole here, that is the original pole in the loop transfer function, okay? Then the time delay introduces a pole here, and then no minimum phase 0 here. What is the effect on the root locus? Now the root locus is not only going to the left to infinity, but now what you have is these two roots that, two poles meet up here in the middle, split off, right? Become complex conjugate, and eventually you know that for high gain, one of the closed loop poles will need to go to the open loop 0, okay? In particular, the open loop 0 is a no minimum phase 0, meaning that the closed loop pole, as you increase the gain, will become unstable, okay? the other root will go to infinity. Okay? So you see that here, even though this is not an exact representation, what you get is the correct qualitative behavior in the sense that now the effect of your time delay is that of making the system go unstable for high gain. Okay? Questions? Hear a lot of buzz, yeah.
The rule for sketching root locus, which tells us that left of an odd number of poles and zeros, we let the root locus on the real axis, and here this doesn't matter.
Anybody knows the answer? Very good, very excellent point.
Can you repeat the answer?
Okay, yeah, so the question was that, I've been telling you so far the rule that I will state it as you said it, which is not what I say, okay? But, so, there is a claim that the rule that we did in class was that, the root locus is on the left of an odd number of poles or zeros. Okay. Is this what I said? And how do you resolve the fact that this is not what I'm showing here? Right, so what I said is that the positive k root locus is on the left of the odd number of poles and zeros. And this is what, this is the reason why I always say, if you want to do root locus, write your transfer function in the root locus form. If you want to do body, write your transfer function in the body form. What is this form? Actually, this form is neither. Okay, so if I wanted to do the root locus, I should write this transfer function in such a way that the coefficient in front of the s is always +1. Okay, how do I write this in such a way that the coefficient in front of the s is +1? Easy. Let's see if this is right. Oh, no, it doesn't write. Come on. Okay, so let's write it by finger. Okay, so you just put a -1, right? So minus s minus 2 over t over s plus 2 over t. Okay? Okay, what you see that now what we have is a transfer function which is written in the root locus form. And what you see is that the gain of this transfer function is actually negative. So if I have a positive k, what is the root locus gain? It's negative. Okay? So, and that's why what we get is this root locus plot. Okay? This particular case, the reality, so the answer to your question really is that, well, the time delay essentially makes you look at the what you would consider the negative k root locus usually. Okay. But it's a very excellent point, and this is this is what you see all the time whenever you have no minimum phase zeros. That you're tempted to write the transfer function in this form, in this form here. And then you forget that there is actually, now you have to look at the negative k root locus, okay? Negative gain root locus. Yeah.
So the condition for stability is the magnitude of k is smaller than 3, or is it k itself?
Yeah. Well, in this case, we are looking at the positive k, which corresponds to negative gain. It is confusing. So if you multiply this by k, oh, come on. I want to write here. Okay. Sorry, this is my fat fingers. So you see that with a positive k, what is the gain in front of the fraction? A positive k gives you a negative gain, right? You get the difference? Because the transfer function itself has a negative gain. No. Can anybody explain it better? Or oh, that's clear. Well, I mean, I don't know. You can see it from here, right? So you just multiply by k this function. There is already a minus in the transfer function, so a positive k will give you a negative root locus gain. Okay? So when you plot the root locus, then you have to look at the negative root locus. Okay? Okay. For me, in summary, yeah, if you really want to use the root locus when using the time delay, you want to use this Padé approximation, which really, I would really see it as more of something that gives you an intuitive feeling for how the closed loop behavior will change given the time delay. But honestly, I will do all the analysis on the Nyquist plot and or the body plot in this case. Okay? But real summary, okay. So what is the effect of a time delay? Anybody?
Exponentially decreasing phase in coding.
Right, which will decrease the phase in the body plot, which translates from the purpose of control design. When you're thinking of your specifications and your closed loop behavior, what is the effective consequence? The real effect. Huh? Right. So, well, I mean, the phase margin. Think of in terms of phase margin, right? Because you have a certain design. Okay. This design will give you a phase margin, will give you a gain margin, will give you a crossover frequency. And the effect of the time delay is to make that phase margin smaller. In one sentence, this is the effect of a time delay. Okay? When I was in your situation, I kept hearing the professors talking about the phase margin, and you want to keep it to make it keep it large enough, and I was always wondering, what the heck is this phase margin? I mean, where is this monster that is eating away my phase margin? Right? And then you realize that actually that monster is the time delay. Okay? Effect of time delay reduce that phase margin. The higher the crossover frequency, the more the phase delay will be. Okay? So let's stop here. It's a nice timing, and let's keep up after the break. Okay? Apple is not cooperating today. Okay. Okay, second part of this lecture, what we look at is some of the factors, how you deal with nonlinearities, okay? So it's kind of funny. You have even experienced, controls engineers that so we have nonlinearities like time delays. No. Time delays are a very linear effect, right? It's a little bit more complicated to deal with. But it's definitely not a nonlinear effect. That said, most real-world systems the reality is that most real-world systems are not linear, okay? In fact, real-world system will be nonlinear. And essentially, if a system is nonlinear, what it means is that you cannot use the principles of superposition. Essentially, you cannot technically use anything that we have done in this class. That technically. In practice, what happens is exactly the opposite. So, typically what you do is, okay, so, this is something that we talk about a little bit about this in the early part of the course. So what you do is you can still write down a model for a nonlinear system, okay? In particular, if you have a time invariant system, then you do not have this explicit dependency on time. So you write dx of dt is equal to some f of x and u, and y is equal to some h of x and u. And then what we do is take the nonlinear system, find the equilibrium point, right? And then we, this is all stuff that we've already done, so that's why I'm going quickly, right? So find the equilibrium point, linearize around that equilibrium point, right? So essentially what you write is that the, let's say psi is the deviation from the equilibrium. This upsilon is the deviation from the equilibrium control, okay? So now you can write your time derivative of this new state variable as something that is equal to 0 plus some matrix, which is actually the matrix of partial derivatives of f with respect to your state variable that multiplies your state increment, plus the partial, and this matrix is something that we call A, right? Plus the matrix of your partial derivatives with respect to the control, which is what we call B, that multiplies your control increment, okay? So what we get is, we have this new state space model, right? Which is given by these matrices A, B, C, and D. We get back to what we have done, what we have covered in the course, right? And essentially we have transformed the, how can we say it? So essentially these matrices A, B, C, D, now these are the matrices that describe a linear system which has no counterpart in the real world. However, this is a linear system that describes very well how the original nonlinear system behaves around the equilibrium point. Okay? You get the subtlety here? This is not real, okay? But it matches very well the behavior of the nonlinear system in the proximity of the equilibrium point, okay? So then what I will do is the following. So I can design my control input, my feedback control. I can say that now my control input upsilon is given by k times c, okay? So that would be a linear control design, okay? And now we say that we assign this feedback, so now the system will evolve in this way. So now the derivative of the state increment with respect to the equilibrium point will be given by f of c comma upsilon, but we know that upsilon is given by k times c, okay? So now what we find is that the derivative of this state is given by some other function of the state, okay? This is the same thing that happens for the linearized version, right? So if in the linear version you just say that, okay, so now my upsilon is given by kxc, you write down the algebra and what you get is this formula, okay? Now, the key point in this is actually something that is shown in an important theorem that is called this Hartmann-Grossman theorem that says that as long as the eigenvalues of this matrix, meaning as long as the poles of as long as the closed loop poles of my linear approximation are strictly in the left half plane, okay, so the real part is strictly negative, then I know that not only my linear approximation will be stable, but also the nonlinear system will be stable, okay? And this is where the power of linear systems and linear control design is to be found, okay? Because this theorem, what it tells me is that, fine, I know that this system is nonlinear. I have absolutely no idea how to design a controller for a nonlinear system. However, I can take this nonlinear system, approximate it as a linear one, use everything that we are learning in this class to design a controller for the linear system, for the linear approximation. And as long as I stay away from the imaginary axis and I keep my closed loop poles in the left half plane, lo and behold, by some magic, that control system that are designed for a linear approximation that does not exist will actually work on the real nonlinear system. You get the whole thing here? Okay? Actually, this is something that is, if you think of it just philosophically, is so powerful, right? And this is the foundation of why we put so much emphasis on this particular class, okay? Because even though you can tell me that in the real world, real linear systems do not exist, but my answer would be, yeah, but I can I can use the linear approximation to enable a whole lot of very powerful design tools, and these design tools will give me controllers that, okay? What you get is, at the end of the day, you get A, B, C, D matrices like this, you get this transfer function, okay? So, not surprisingly, the speed dynamics of a car are typically a first-order system, okay? Which you may have noticed, right? So what happens if you're driving at a certain speed and then you press the gas pedal by some angle? Your speed will pick up quickly at the beginning and then will stabilize at some new value, right? Will it typically oscillate? No, right? You press the pedal, the car accelerates, period, okay? What is the time constant? Well, in this case, is this number here that depends on, your gear ratio, aerodynamic force, your speed, and so on and so forth, okay? Simple first-order lag. We know that just a proportional controller will stabilize the system. However, proportional controller, what will happen if a proportional controller, now I have a slope, right? So now I'm going uphill. Now, instead of keeping the desired speed of, say, 100 kilometers an hour, I'm going uphill, the car will tend to slow down. How do we fix that? How do we maintain a zero steady-state error to a unit step in a disturbance, for example? Is by adding an integrator, okay? So, in this case, a PI controller will work. We can choose this particular structure for my controller. And, okay, so this is what, if you do it in Simulink, if you really want to do it in Simulink, this is what it will look like, okay? And in particular, what I did in this case is the upper block is actually the nonlinear model of the car, okay? The lower block is actually the linearized approximation, okay? And I want to compare the two, okay? This is actually what you see, out of, I simulated the fact that now I have a 4-degree slope, like a 7% slope, okay? Okay, and what you see in the picture above is actually the speed, okay? So what you see here is that because I had the integrator, even in the case in which I have the slope, what you see is that the speed will go back to my desired value, in this case 25 miles an hour, okay? Okay, now I don't remember which one is which, but you see that the two curves are actually, both the nonlinear system and the linear system, the linear approximation, behave in pretty much in a similar way, okay? What you see below is actually the, the value of the control input, okay? So you see that the value of the control input, they differ by a little bit, okay? But this is exactly why you like feedback. Because when you have feedback, you don't need to have a very precise model of how the system will behave, because your feedback will figure out what it needs to do in order to make your system behave the way you want, okay? Okay, so far so good, okay? And, this is, the way it works. The nonlinear system, compute approximation, design for the approximation, applied on the nonlinear system, and things work. Except in a few cases, okay? So there are a few cases where you need to be a little bit careful, okay? And you have to do something a little bit more. And, one of the things that I said is that the nonlinear system will also be stable as long as you remain in the vicinity of your equilibrium point or your equilibrium operating condition. Okay? Now, something that may happen, for example, on a car is the following. Now, your slope is increasing, okay? And now, yeah, your feedback controller is saying, okay, so I'm slowing down, so your integrator is, building up, right? So, and then you start pressing the gas pedal more and more and more. But now let's say they're going through a very steep incline. Maybe there is, and you may, okay, you're driving a normal car, you're not driving a Lambo or something, right? So, so let's say that maybe your car is just not capable of going at 100 kilometers an hour on a very steep hill, okay? So what happens in that case? Okay, so in reality, for example, what is the difference, right? So in your real system, in the linear approximation, there is no bound on how much you can choose U, right? How large you can choose U, right? You can choose your control input to be as large as you want. In reality, sorry, your maximum torque, your maximum power of your engine is this much, right? And I cannot increase it beyond a certain limit. Okay, so this is something that is called the saturation. Okay, so what you see the effect of the saturation here is the following. Okay. So, okay, so now purple is the response of your linear approximation, okay? So look at what happens in this case. In both cases, as soon as you hit the slope, the speed will decrease, okay? However, the integrator kicks in, and then you see that in the nominal case, in the linear case, the speed will go up, and then nicely go back up to your desired speed. Look at what happens to the real nonlinear case with the saturation. Okay, what we have is that the speed goes down, then the integrator kicks in, right? And then the speed starts going up, but then you see that, okay, you get back to your desired speed, but your car keeps accelerating, right? And you see that your car keeps accelerating and actually starts going to some higher value of speed before settling down to what you want, okay? And, I mean, you cannot say, well, sorry, officer, it was my cruise control, right? So that's something that you don't want. Now, what is happening? Why do you have this peak for the nonlinear controller? You can get a sense of what is happening by looking at what is happening to the control input, right? So what you see is that the linear approximation, the control value is happily, goes to some, say, very large value, okay? But in reality, your maximum control in this case is 1, okay? So now your control system will try to say, push that pedal, right? But the pedal is reaching the limit, and there is not much that you can do, okay? So now what is happening in your integrator? You're pushing on the pedal, you're trying as hard as you can to match the speed, the reference speed. You just cannot do it, okay? And then the integrator, the error in the integrator keeps integrating, right? So keeps building up, right? Even though there is nothing you can do, it keeps building up, right? And so even at the point where you actually finally match the desired speed, the error in the integrator is still very large, okay? And that's why the integrator will keep you pushing, keep the speed up, okay? So how do you fix that, right? So essentially, once the input saturates, the integral of the error keeps increasing, and there is nothing you can do about it, okay? Because that's the highest control action that you can apply, okay? So then this large integral prevents the controller from resuming normal operations once you get close to the reference point again. Okay, so how do you fix it? Essentially, the basic idea in this case, okay, so this phenomenon is something called the integrator wind-up. Okay, so you have this integrator that keeps charging up, okay, even though there is nothing you can do to prevent that charging up, okay? So then the idea to prevent this wind-up is actually a very simple one. So something that you can do is whenever you see that your input is saturating, stop integrating the error. Okay? Sorry, there's nothing I can do, so stop blaming me at this point. Okay? Stop getting mad, just give me a break until we get to a point where I can actually do something. Okay? And this is how you, okay, so something that you can do is use as the, as the integral gain, say, set it to your actual desired integral gain if the input does not saturate, or set it to 0 if the input saturates. You can do it. It's not that elegant. This is actually a more elegant solution, which essentially you do the following. So just compare the actual input they're able to give, so the saturated input, and the linear input, and the ideal input, okay? If they're the same, essentially their difference is 0, then there is no saturation. If they are different, then there is some saturation, okay? And then you can reduce the integral error by a constant times the difference, okay? So under this choice, whenever you're saturating, the integral error behaves like a simple lag and converges to 0, okay? You're saturating, eventually your integral error will converge to 0, saying, well, okay, it's nothing I can do, so stop getting mad, okay? So just accept the fact that you cannot meet that particular reference, okay? If the linear input and the saturated input coincide, that is, the linear input is below the saturation, then this thing has absolutely no effect, okay? So how do you draw it? This is something that, so essentially what you see is here, okay? So you had the saturation. So this is the saturation block, okay? And so what you see here, at this point is the ideal control input, right? So this is the control input that I would like to have. Right after the saturation block is the input that I can apply, okay? So what I will do, I will subtract them, right? I will compare them, multiply them by something, and this is by how much I reduce the integral error, okay? So this is called an anti-wind-up scheme, and, for example, this is, how it will work, okay? So essentially what you will see is that at the time where the input is saturating, you stop getting mad, with the integrator. You stop winding up the integrator, and as you can see, there is no longer that big peak at the end of the, before you settle down to the reference value. Okay, so I wanted to say this because very often when you design a system, you want to have the 0 steady state error, you are typically tempted to put an integrator in there. However, the integrator can generate very bad behavior whenever your system is subject to saturations. Okay? So, word to the wise, every time you are designing a control system with an integrator in a real-world setting, make sure that you also add this anti-wind-up scheme. Okay? So make sure that your integrator doesn't just go to crazy values just because your input is saturating. Okay? Okay? Got the point? Well, I mean, this is done very early today, so we can get started on the next one. Okay, so in summary, anti-wind-up schemes guarantee the stability of the compensator when the original feedback loop is affected by saturation. What is the effect of saturation, right? So once your input saturates and you're pushing your pedal to the metal, right? Essentially, you're removing the feedback because at this point, there's nothing you can do, right? So the pedal will not move. The speed can change, you will not be able to change the pedal, right? So the effect of the saturation is, in a sense, to open the feedback loop, okay? In that case, the integral error can diverge, right? So get very large, can wind up. So what you want to do is make sure that the integral error does not saturate, does not grow when your input is saturating. Okay? Okay. Good. As I said, it's early, so maybe we can get started on material for next time, unless there are any questions. Or maybe we can take this time to answer, general questions that you may have. Let's do this. So, anybody has questions about anything in the course? Back in September, you said this. Nothing? Okay, so then start looking at, give me a second, I will get the material from the next lecture. Okay, just give me 1 second. Think of any questions you may have, okay? In case. So everything is clear. Oh, yeah.
If we have multiple integrators, how would we prevent the wind-up of integrators?
Okay, so the question is, how would you prevent the wind-up of integrators if you have more than one? Well, you do the same for every one of them, right? So essentially what you want to do is you want to avoid having any integrator building up error when there is nothing you can do about that error. Okay, so this is the idea. It's exactly the same. It's exactly the same. So just reduce the integral error whenever you're saturating. Yeah. Okay, so, well, this is material from the last year's lecture, but it's the same for this year. But, okay, so essentially what I wanted to do in the last lecture is to talk about two things. One is this idea of robustness, and the other one is how do you actually implement these things in real life, okay? So where do you get an integrator, okay? Where do you buy an integrator? How do you make one, okay? So let's talk about this, this idea of robustness, right? So what is the idea? And, in a sense, we touched upon it when talking about nonlinear systems. So the reality is that whenever we write a model, be it a linear model or even a nonlinear model, you have to accept the fact that that model is not reality, okay? Actually, I was having a discussion with one of you before that apparently the model that you are, that is proposed in the notes, in the exercise notes, may not be a good model for the seesaw, right? So, but this is true in general, right? So whatever model you write for anything is not reality. Okay, the only model for reality is reality. Right? So, okay, so that's the only accurate one. Okay, so even if you have a very precise model, which, by the way, is something that you don't necessarily want, the model will not be the same as actually doing the real experiment, okay? So, why is it the case? Well, very often, for example, it may be difficult for you to capture, exactly the data, from the behavior of the system because of measurement noise, or maybe just the behavior of your system is so complicated that it cannot be captured with the model that you are able to handle, okay? The point is that even though you have to accept the fact that your model is not the same as reality, what you want to do is design a control system for your model knowing that it's not precise, it's not exact, and you want to make sure that your control system will behave well, not only for your model, but also for the real system, okay? How do you make these things kind of precise? The idea is the following. So what you do is is this. So let's say that you have the real system. The real system is something that you don't know, okay? Period. You just don't know what it is. However, you can design a nominal system, okay? So this is your model, okay? And then I say, and think of this piece of, this slide as the set of all possible dynamical systems, okay? So then what I'm saying is that I don't know where my real system is, but I know that my nominal system is here, and the real system is not too far, according to some metric, from my model, okay? You see the subtlety here. So I know that my model is not the real thing, but I know that my model is not too far away from the real thing, okay? Where too far away is to be defined in a certain way, okay? So then what I will do is I will design my control system in such a way that not only it works with my nominal model, but it works for all possible other models that are within this uncertainty bound, okay? And that's why you want to have this, for example, the phase margin, right? So the phase margin is one possible representation of uncertainty, right? So what I know is that maybe my model, my real system will not be the same as the model, right? But as long as the phase delay is no more than the phase margin, then I'm okay, right? So now the real system may include things like a time delays, but as long as the time delay is not more than my phase margin, then I'm okay, okay? And so what we will do in the rest of, for the few slides and next time is look at what are some common uncertainty models for CISO systems, okay? These are all methods that aim at writing the transfer function of the real system as one that is a nominal transfer function, okay? Times or plus some unknown transfer function delta, which represents the uncertainty, okay, as a perturbation to my nominal system, okay? Now, the way that we represent delta is something that we assume it's a stable minimum phase transfer function, and that does not cancel the unstable poles of the nominal system, okay? Also, what we will do is we scale the perturbation in such a way that the magnitude of the perturbation is always less than 1. You can always multiply by some k, okay? So then what we will do is, if you remember, we introduced this idea of these frequency weights when we are talking about the obstacles on the body plot, okay? So even in the case in which we have the uncertainty is given by some complicated transfer function, we can always write it as some function W2 multiplied by this delta, which this delta is something that we know is in magnitude between -1 and 1, okay? Okay, so these are like a frequency weights, okay? So the first kind of uncertainty is something that's called like a multiplicative uncertainty, okay? So multiplicative uncertainty is something of this form. So what you have is your nominal transfer function P, and then in order to get your real, okay, but this is unknown transfer function, this is something that's given by P multiplied by 1 plus this uncertainty term. Okay, so this something is called the multiplicative uncertainty. You do the algebra, what you find is that the ratio of my real but unknown transfer function over your transfer function -1 is limited, is bounded by this frequency weight W2. Okay? So essentially the multiplicative uncertainty model is a description of how the ratio of the real and nominal transfer functions are away from being 1. Okay? When do you use this? Essentially, multiplicative uncertainty is useful when the gain of your real transfer function is uncertain, is unknown, okay? For example, if I know that my real transfer function is given by some unknown gamma times some transfer function g, okay? But I do not know, yeah?
One slide before.
Yeah.
How do you exactly know W2 of J omega?
Yeah, so this is what you get out of your, we'll do an example, okay? So essentially this is, so essentially when you're designing your nominal model, you also want to know by how much you think that you're missing the real one, okay? So in this particular case, we know that the real transfer function, which we do not know, is given by some gamma that multiplies some transfer function g that we know, okay? We do not know what gamma is, but we know that gamma is between two numbers, okay? I don't know what the weight of the, of the luggage in the trunk of my car is, but I know that it will be between 0 and 500 kilograms, okay? Okay, so this is how you set this, the W2, essentially, right? So G is a non-transfer function, so now we can represent the same set of systems by using multiplicative uncertainty by setting, okay, so let's choose gamma naught to be the mean value of my bounds for gamma, okay? So now my nominal transfer function will be given by that average value of gamma, so my luggage in the trunk will weigh 250 kilograms, okay, times my non-transfer function, okay? And then omega 2 will be given by this quantity. So essentially, sorry, this should be a minus. So essentially, this is the difference between the two bounds over the sum of the two bounds, okay? So then you can verify that if I use an uncertainty, the multiplicative uncertainty model with this omega 2, will actually allow me to capture all possible real plans, even though I do not know exactly what gamma actually is, okay? So we didn't talk a lot about this, but for example, how do you get the transfer function of your system? What we typically do in class is, okay, so somebody gives you the transfer function, right? Or maybe you write down a model and you compute the A, B, C, D matrices, you compute G of S is equal to C times Si minus A inverse B plus D, blah, blah, you compute the transfer function. In reality, that's not typically what you do. Typically what you may do is you get a system, for example, you get your seesaw, don't believe what the TAs are telling you, and don't believe what the professor is telling you, right? But take the system and apply a sinusoid, okay? And you will get, we know that if you apply sinusoid, your system is stable, you will get another sinusoid with different frequency, different amplitude. Sorry, the same frequency, different phase, and different amplitude. And what you can do is plot, just give a frequency 1, 0.1 hertz. Apply it, see what happens to your system. Try 1 hertz, try 10 hertz, try 100 hertz, right? And you will get a bunch of points that allow you to say, okay, at this particular frequency, the amplitude of the output was this much, and the phase of the output was this much, okay? And you put them on this, essentially, on the body plot. Now, since you're running a real experiment, your curve probably will not be like a nice, smooth curve, right? So this would be a bunch of points that are kind of somewhat scattered around something real, okay? And you see what is happening here. For example, what you can say is that, in this region, it is pretty clear what the magnitude of the response is, right? So you see that the variance of the measured responses is very small around some, centered line, right? So some approximation. However, you see that in this range, you see that there is a much bigger variability, okay? So what you see that in this range, what you have is a much less certainty about what is the gain of your transfer function, okay? And that's a perfect place to use this multiplicative uncertainty noise model, okay? So essentially what I'm saying is that, well, in this frequency range, I don't really know what the gain is, but I know that will be between, say, here and here, okay? So it's not that it's completely unknown. It will be somewhere in this bound, in this range, okay? And, this is also, how you can represent it in a block diagram, okay? So this is what the true unknown transfer function looks like. This block diagram is something that will give you exactly the same transfer function, okay? So you can imagine that in the case in which you had zero uncertainty, it's as if you were ignoring the block, the upper part, this part of the block diagram, right? This is your nominal model. Add the uncertainty, you add this part, okay? And now what you want to do is make sure that this system is stable no matter what delta actually is, okay? But let's keep talking about this next time, okay?